In this video, we are going to see the concept of probability. Under this, we are going to learn sample space and events, the concept of probability, axiom of probability, and some elementary theorems. Before we start the probability, let us understand what is the random experiment. A random experiment, if its outcome cannot be predicted with certainty. For example, if a coin is tossed, we cannot say whether head or tail will appear. So, it is a random experiment. When we perform an experiment, we know all possible outcomes of that experiment. But the outcome of that experiment we don't know. We cannot predict. In the example as we give here, when you toss a coin, you know that it may appear head or tail. You know the all possible outcomes of that experiment. But you cannot say head may appear or tail may appear. Now this kind of the experiments are called random experiments. Sample space. What is the meaning of sample space? The set of all possible outcomes of the random experiment is called the sample space. Sample space means the set of all possible outcomes of the random experiment is called the sample space. It is denoted by capital S and its number of elements are n of s. The total number of elements in the sample space, which is represented by n of s. For example, in throwing a die, the number that appear at the top is any one of 1, 2, 3, 4, 5, 6. So, here, sample space S equal to the set of 1, 2, 3, 4, 5, 6 and n of s equal to 6. Similarly, in the case of the coin, sample space head and tail, n of s equal to 2. Each element of sample space are called sample point or event point. Now, each of the element of sample space is called a sample point or event point. Now, sample space means the set of all possible outcomes of the random experiment. That is the sample space. Next, event. Every subset of sample space is an event. It is denoted by capital E. For example, if you toss a coin, the sample space is capital S equal to head, tail, but event. You are looking for one event, the event of getting head or the event of getting tail. That is called one event. H is subset of sample space, the set H, T. T is also subset of H, T. Here H, T is also the subset of the set capital S, H, T. Here example, in throwing a dice, sample space set, which is 1, 2, 3, 4, 5, 6, the appearance of an even number be the event E equal to 2, 4, 6. Clearly, E is a subset of S. Now, when you throw your dice, the sample space you know very well, which are the set of 1 to 6 numbers, the appearance of the even number, the appearance of an even number will be the event. Getting the even number is an event. There are Three possibilities are there: 2, 4, and 6. This event is a subset of capital S. An event is subset of sample space and which is denoted by capital E. Simple event. An event consisting of a single simple point is called a simple event. For example, in throwing a dice, the sample space is 1, 2, 3, 4, 5, 6. So, each of 1, the set 1, the set 2, the set 3, set 4, and so on, set 6 are simple events. Now, in the event consisting of single sample point is a simple event. Compound event. A subset of the sample space which has more than one element is called a mixed event. A subset of sample space which has more than one element is called a mixed event. For example, in throwing a dice, the event of appearing of odd numbers is a compound event because E equal to 1, 3, 5, which has 3 elements. The 3 elements are more than one element in the event. Now, this kind of the events are called compound events. The event that you are getting an even number is also compound event. Next, equally likely events. Events are said to be equally likely if we have no reason to believe that one is more likely to occur than the other. Example: when a dice is thrown, all the 6 faces are equally likely to come up. Now, there is no reason to believe that. If you take the event, for example, one event, it is the one outcome. 2 event, getting 2 is the one event. Like that, you get the 6 faces are equally likely come up. When you toss a coin also, the head and tail are equally likely to come up. Exhaustive event. When every possible outcome of an experiment is considered, then that event is known as exhaustive event. For example, a dice is thrown, cases 1, 2, 3, 4, 5, 6 form an exhaustive set of events. Now here we are considering outcome of an experiment, every possible outcome of an experiment. That is a exhaustive event. Mutually exclusive or disjunct event. If 2 or more events cannot be occur simultaneously, that is, no 2 of them can occur together. If 2 or more events cannot occur simultaneously, that is, no 2 of them can occur together. These kind of the events are called disjunct events or mutually exclusive events. Example: when a coin is tossed, the event of occurrence of head and the event of occurrence of tail are mutually exclusive or disjunct event. When you toss a coin, there is a possibility to get either head or tail, but these 2 events cannot occur simultaneously. Independent or mutually independent events. 2 or more events are said to be independent if occurrence of or non-occurrence of any of them does not affect the probability of occurrence or non-occurrence of the other event. The one event does not affected. One event is not affected by the another event. That kind of the events are called independent events. Example: when a coin is tossed twice, the event the event of occurrence of head in the first thrown and the event of occurrence of the head in the second thrown are independent event. When you toss a coin for 2 times, now the event of getting head is independent. The second trial also, the event of getting head is a head is which is independent. Now these two events are independent events. Complement of an event. The complement of an event A with respect to capital S is the subset of all elements of S which are not in A. We denoted the complement of capital A by the symbol A prime or A complement. The complement of an event A. If you take the sample space capital S, if you take the sample space capital S, this is the sample space on where A is the event which is subset of sample space. This is the sample space. A complement. This is, wait a minute. Now, when you take the sample space capital S like this is the sample space capital S. Now this is the event capital A. The remaining, this is all this area is going to be complement of A. Now the complement of an event capital A with respect to capital S is the subset of all the elements of S which are not in A. We denoted the complement of A by the symbol A prime or A complement. For example, let A be an event that an even number of dots occur when a die is rolled. Then A complement is an event that an odd number of dots occurred. You are taking the A is the event which is the odd number of dots, and A complement is even number of dots. Next, intersection of two events. The intersection of two events A and B denoted by the symbol A intersection B is the event containing all the elements that are common to A and B. Example, let C be the event that the students selected at random that are of the second year, and M be the event that students are boys. Then C intersection M is the event of all second year boys. Union of two events. The union of two events A and B denoted by the symbol A union B is the event containing all the elements that belongs to A or B or both. In die rolling experiment, if A equal to 3, 6 and B equal to 2, 4, 6 and A union B equal to 2, 3, 4, 6. These are the elements which are in either A or which are in either B or both of them. And it is represented the event of getting an even number or a multiples of 3. some of the following result can be observed. A intersection pi equal to pi, A union pi equal to A intersection A complement equal to pi, A union A complement equal to S complement is pi complement is S, and A complement whole complement is A intersection whole complement equal to A complement union B complement, A union B whole complement equal to A complement intersection B complement. These are the some results we are going to use in the problem sessions. Classic definition of probability. If S be the sample space, then the probability of occurrence of an event is defined as P of the probability of the event P of E, which is equal to N of E divided by N of S, where N of E is number of favorable events and N of S is total number of exhaustive events. This is the classical definition of the probability. Capital S is a sample space, we are going to take it. Then the probability of occurrence of an event. From the sample space, we are going to select some event. The probability of getting that event is defined by the number of favorable events divided by total number of exhaustive events. Axiom of probability. Now the probability function P is defined on subset of the sample space capital S to satisfy the following axioms. Number 1. Non-negative probability. Always the probability is going to be a positive value. The probability value always is greater than or equal to 0. Sometimes it may be 0. Now the probability value is always positive. Second one, mutually exclusive events. Mutually exclusive means if you take the two events A and B, A intersection B is empty. For the mutually exclusive events, P of probability of A union B, which is equal to probability of A plus probability of B, provided A and B are mutually exclusive, which means A intersection B is empty. The universal set P of S equal to 1. The probability of the sample space is equal to 1 always. That means the probability of any event is going to be lies between 0 and 1. These are the axiom of probabilities. Very, very important properties. Example 1. A box contains 25 parts, of which 10 are defective. 2 parts are being drawn simultaneously in a random manner from the box. The probability of both parts being good is, now in a box there are 25 parts are there, of which 10 parts are defective. 25 parts, there are 25 parts are there. First we are going to write down number of parts. The number of parts are 25. Defective one are 10. This is the total, or this is the defective, or the good one. Good one are, this is 15. Total parts, defective parts, and good parts. Now like this we are going to classify this. So listen, how many parts we drawn simultaneously? Now the number of ways drawing 2 parts. This is the exhaustive event from 25 parts. The number of ways drawing 2 parts from 25 parts is 25 C2. 25 C2. The number of ways of drawing 2 good parts from 15 good parts. From 15 good parts, which is 15 C2, which is the favorable event, which is the total number of events. From the classical definition of the probability that both parts are good. Here the favorable event is the getting a good parts. The event which is getting the good parts. The number of days getting the good parts is 15C2 divided by 25C2, which is equal to 7 by 20. Answer is this. Next example. An unbiased coin is tossed an infinite number of times. The probability that the fourth head appears at the 10th toss is. The fourth head appears at the 10th toss is. Now, we are tossing a coin for infinite number of times. The probability that the fourth head appears at the 10th toss. That means before that 3 heads must be appear. This is when you toss a coin first time, it may be tail. The second time, it may be head. Third time, it may be again the tail. Fourth time, again it is tail. Fifth time, again it is tail. Sixth time, again it may be head. Seventh time, it may be tail. And eighth time, it may be head. And the ninth time, it may be tail. The fourth time must be, it will come head. Before that, how many heads has to be happen? 3 heads has to be happen. In 9 trials. Before you are performing the 10th trial, you must get at least 3 heads. Minimum 3 heads you must get, so that you are going to get at the 10th trial, you are going to get the head. What is the probability of getting that head at the 10th toss, which is head? Let us see how many times we are tossing a coin. Now you are tossing a coin for 10 times. Now the number of possibilities of the first 10 slips, which is 2 power 10. 2 power 10 is, this is the 1024. If you toss a coin, how many possible one time, how many possibles are there? There is the 2 power 1 possibility is there, one time. If you toss a coin, how many possible? 2 power 2, which are, this is head and tail. Right? It is the 2 power 2 means 2 times you are going to toss a coin. It may be shows head and tail for one time. The second time also it may be shows the head and tail. Like this. Okay. Now like this way we can get the for 10 times we are going to get 2 power 10, which is going to be equal to 0, 10, 24. Now these are the values we are going to take it. For the fourth head occur on the 10th slip, we need first 3 heads to occur in the first 9 slips. This is given by 9C3 ways. We are getting the 3 heads before we are tossing the 10th time. That is, you must get the 3 heads. That is the 9C3 ways. You can get the head. 84 ways. Now, there is only one way for fourth head occur on the 10th slip, which is 84 divided by 1024. The favorable events are 84 and total events are 1024. When we cancel all these things, then we will get the probability 0.08282. This is the probability. Now, like this, we will get the probability. These are some examples of the probabilities. In the next, we are going to see next example. In rolling a pair die once, what is the probability P of A obtaining a 5 or a 6? The probability of P of B of even numbers. Now, in the first problem, we have to get P of A, that is, the event we are getting either 5 or 6. Probability of getting 5. The sample space we know. When you roll a die, that is the sample space, which is equal to 1, 2, 3, 4, 5, 6. This is the sample space. Now for this sample space, Now we are to looking for the first probability P of A. What is the probability of getting either 5 or 6? Either or means in the probability we are going to take in the union. That is union. Or union means which is in the probability plus. Now the symbol either or. Or means union which is plus. These are the all three are equal in the probability theory. Now first we identify what is the probability of getting 5. These are the all sample, this is the sample space. Out of this, there is only one possibility to get the 5, that is 1 by 6. Now, what is the probability of getting the 6? This is 6 here, 1 by 6. The probability of getting 5 or 6 is P of A. Let us define the event A. We are getting either 5 or 6, which is equal to 1 by 6 plus 1 by 6, which is 2 by 3. Then probability of getting the even number is denoted by P of B. The P of B is denoted the probability of even number. Now you are looking for the event B is 2, 4, 6. These are the even numbers. Your favorable events are 2, 3, 6. How many events are there? This is 3 events are there. The favorable event, the number of favorable events divided by total number of sample space events, which is 3 by 6, which is equal to 1 by 2. Right. Like this, we are going to get the probability of these two answers. In the next we are going to get it. Say, from the example 4, from the pack of 52 cards, 2 cards are drawn at random, then find the probability that one card is of diamond and the other is of the spade. Now there are 52 cards are there in the pack of cards. Find that probability one card is of the diamond and the other and means here is the and we are going to use it. In the previous problem, here use the or. Here we are going to use the and. A and B. And. And means intersection. And means intersection. Intersection means multiplication. Okay. In the probability theory, and stand for the intersection. And intersection means we have to multiply the things. Okay. Or means we have to add the things. Intersection means we have to multiply the things. Solution. Let this S be a sample space. Now, how many ways you can select the 2 cards from the 52 cards, which is N of S. N of S equal to, I can select the 2 cards from the 52 cards in 52 C2 ways. Now, when I solve this one, 52 C2, that is 52 into 51 divided by 2 into 1, which are 13, 26. This is the sample space. That is N of S equal to 1326. Now, let us define an event E. Event E, event of getting one diamond and one spade. One diamond and one spade. How many diamonds are there in the total cards? There are 13 diamonds are there. 13 diamonds. 13 spades, like this. Here I show the figure. 13 diamonds. 13 spades. 13 hearts, 13 clubs. These are the items are there in the pack of cards. Now there will be 13 diamonds are there. There will be 13 spades are there. Now we have to select one diamond and one spade out of 13. One diamond out of 13 diamonds and one spade out of 13 spades. You have to select. How many ways you can select? One diamond out of 13 ways. That is the 13 C1 ways you can select first one. Then one spade out of 13 spades you have to select. In how many ways you can select? That is 13 C1 ways. 13 C1 is 13. We know. 13 C1 is again 13. 13 into 13 is 169. This is the favorable events. Out of all these events, how many favorable events are there? 169. By the classic definition of the probability, the P of getting one diamond and one spade, which is equal to number of E divided by number of S. Here number of E is the 169 and number of S is 1326, which is equal to 13 by 102. Like this, we are going to find out the probability of the getting one diamond and one spade. Let us look into some properties of probability. Here the probability of the impossible event, which is P of pi equal to 0. That means there will be no events. That kind of the event, when you take the probability of that event, is 0. If A complement is the complement of the complementary event of A, if A complement is the complementary event of A, then P of A complement equal to 1 minus P of A, which is less than or equal to 1. Addition theorem and probability. If A and B are two events in a sample space capital S, then P of A union B equal to P of A plus P of B minus P of A intersection B. Here A intersection B is not equal to pi. Here A intersection B is not equal to pi, like this, which is non-empty. Very similarly, when you take the addition theorem on three events, if A, B, C are the events in a sample space capital S, then P of A union B union C equal to P of A plus P of B plus P of C minus P of A intersection B minus P of A intersection C minus P of B intersection C plus P of A intersection B intersection C. This is for the formula for the three events for the addition theorem. Now, if A and B are two mutually exclusive events, that is, A and B are design sets, A intersection B is empty, then P of A union B equal to P of A plus P of B. Then P of A intersection B, which is P of pi, P of empty set is equal to 0. If A, B and C are three mutually exclusive events, then P of A intersection B intersection C, which is equal to pi. If A, B and C are three mutually exclusive events, that is A intersection B intersection C, which is equal to empty set and pi. Then P of A union P union C, which is equal to P of A plus P of B plus P of C. Then if A1, A2, and so on, AN are mutually exclusive events, then P of A1 union A2 union A3 union and so on union AN, which is equal to P of A1 plus P of A2 plus and so on plus P of AN. Example 1. Consider randomly selected a student in a certain university. Let A denote the event that selected individual as a Visa card and B be the analogous event for a MasterCard. Suppose that P of A equal to 0.5 and P of B equal to 0.4 and P of A intersection B equal to 0.5. Then, number 1, compute the probability that selected individual has at least one of the two types of cards. Second, compute the probability that the selected individual has either type of cards. Number 3, describe in terms of A and B the events that the selected student has a Visa card but not a MasterCard, and then calculate the probability of that event. Now here the problem has given very clear. Let A be a event, the student which is having the Visa card. B is the event, the student which is having the MasterCard. Is having the he has given the A intersection B also. Probability of A intersection B, it is 0.25. He has given the probability of having Visa card is 0.5. The probability of having MasterCard is 0.4. The probability of having both cards are 0.25, which are given in the problem. But we need to compute the probability that the selected individual has at least one of the two types of card. At least means he may be have the 0 cards, he may be have the 1 card, or he may be have the 2 cards also at least. Okay. Now the solution is consider randomly selected student is at a certain university. Let capital A denote the event that the selected student has a Visa card and B be the analogous event for a MasterCard. Suppose that P of A equal to 0.5 and P of B equal to 0.4 and P of A intersection B equal to 0.25. The probability that the selected student has at least one of the two types of cards, which is equal to he may having the 1 card or 2 cards. Now we know that P of R, I am using the R, which is the which means union. You have to take it. P of A union B equal to, by the addition theorem we know that P of A union B equal to P of A plus P of B minus P of A intersection B, which is equal to, now P of A is which is 0.5 and P of B is which is 0.4 and P of A intersection B equal to 0.25. When you substitute all this in the formula, when you substitute all these values in the formula, then you will get the total probability is 0.65. Continued. The second question is asking the probability that the selected student has neither type of card. He does not having any type of the cards. That means we have to select here P of A union B is a having any one of the card. Neither here has neither type of card. That means you have to take it A union B whole complement. You have to take it. These are A union B is what is a student has either Visa card or MasterCard. Now neither card means you have to take the complement of this one. The student who does not having any type of the card, that is called as a neither type of card. That is, you have to compute probability of A union B whole complement, which is the probability of the complement. We know that which is equal to, you can consider this is as a E, A union B whole complement. This is A union B as a that is E, P of E complement equal to 1 minus P of E, where E is nothing but P of E is nothing but A union B. Like this, you can understand the problem. That is, you have to compute. So you know P of A union B in the previous problem. That is, we are going to substitute here. Now we will get the student, the selected student as neither type of card, which means now as I explained, P of A union B whole complement, which must be equal to 1 minus P of A union B. That is 1 minus, we know that P of A union B from the previous one, that is 0.65. When you subtract 0.65 from 1, you will get 0.35. The third one is asking that the event that the selected student has a Visa card but not MasterCard. The selected student having Visa card but not MasterCard. Having Visa card, which is the event, capital A, not having the MasterCard, which is having the MasterCard is B, not having the MasterCard is B complement. Understand? The student having Visa card but not a MasterCard. Now what you have to do is the student having Visa card and now they having MasterCard. And you have to use the AND symbol here. AND means you have to multiple the probability of having A and the probability of having this one. How we are going to get it? This is P of A intersection B complement. We are using the formula P of A equal to, from this formula we are going to identify how we are going to get it, which is P of A intersection B plus P of A intersection B complement, which is P of A. The formula for the P of A, only the card is having the Visa card, which is that is equal to P of A intersection B plus P of A intersection B complement. From this, this is A intersection B is the student having the both cards here. Here this is the student having the only Visa card but not the MasterCard. This is the formula, the student having only the Visa card. Only Visa card. Okay. From the students, those who are having all the cards, okay, Visa card as well as the MasterCard, and the student having only the Visa card also. This is the P of from this we are going to write down P of A intersection B complement. That is the student having Visa card but not having the MasterCard. This is the P of A means the student who is having all Visa cards only is having the only Visa cards. Okay. Now which is equal to, this is P of A. Now this is you have to send to the left hand side, which is P of A intersection B. This is the formula we are going to use it. From this formula we are going to write down, which is the same formula I have written, P of A intersection B complement, which is equal to P of A minus P of A intersection B. Now you know P of A. What is P of A? 0.5, and P of A intersection B is 0.25. When you subtract 0.25 from the 0.5, you get the 0.25. Like this. That is now 0.525 is the probability that the student, the selected student, who is having Visa card but not have the MasterCard. Now, next we are going to see the example 2. It is the example 2 for the given P of A equal to 0.35 and P of B equal to 0.65, P of A intersection B equal to 0.12. Then compute number 1, P of A union B. Number 2, P of A complement intersection B complement. Number 3, P of A complement intersection P of A complement intersection B complement. This is what we have to find out. First we are writing whatever the given values he has given. First let us note it down, all the values which are given in the problem. The given values are here. First I know that P of A is given, which is 0.35, and P of B we know, which is 0.65, and as given P of A intersection B, which is 0.12. Now first we have to find out P of A union B. By the addition theorem we know that P of A union B equal to P of A plus P of B minus P of A intersection B. Now here P of A and P of B, all the values we are going to substitute, which is equal to P of A is 0.35, P of B is 0.65, and P of A intersection B is 0.12. Now when you solve this, then we will get the probability, that is P of A union B equal to 0.88. The second one is P of A complement intersection B. As in the previous problem I explained, it is the probability of B but not A. The probability of B but not A. How the formula is going to be derived? The probability of this is C, P of B equal to, now I written the formula here very clearly, only B, that is P of A complement intersection B plus P of A intersection B. This is the only B. Now from this, B but not A, that is you have to compute. From this, we are sending this to the left hand side. This P of B comes to the right hand side. Now when you rewrite the equation, P of A complement intersection B, which is equal to P of B minus P of A intersection B. Now we know that P of B is 0.65 and P of A intersection B is 0.12. When you subtract 0.12 from 0.65, you will get it answer 0.53. Third one, you have to get it P of A complement intersection B complement. How we are going to get it? P of A complement intersection B complement. Now we know that how by the De Morgan's law, we know one formula, that is A union B whole complement, which is equal to P of A complement intersection B complement. Now this is the De Morgan's law. Now from that we are going to find out P of A union B whole complement, which is equal to P of A complement intersection B complement. P of A intersection B complement, which is nothing but 1 minus P of A union B. 1 minus P of A union B, which is very simple. Here I am going to write down P of A union B, A complement intersection B complement. By the De Morgan's law, this will become A union B whole complement. Let's understand that the De Morgan's law, A complement intersection B complement must be equal to A union B whole complement. A union B whole complement is nothing but 1 minus A union B. When you apply the probability on each and everything, this is the P I am going to apply, P of this and P of this and P of this. The answer is very clear. Now, if you want to find out the P of A complement intersection B complement, it is sufficient to find out 1 minus P of A union B. Now from here, now you know what is the P of A union B. From here, 1 minus P of A union B is 0.88. Already we calculated in the first part. That is 0.88. We are going to substitute here. Now, when you subtract 0.88 from 1, you get 0.12. This is the answer for the third question. In the next slide, in the next example, we are going to see the route used is certain motorist is commuting to work contain two intersections with traffic signals. The probability that he must stop at the first signal is 0.4. The analogous probability for the second signal is 0.5. And the probability that he must stop at least one of the two signals is 0.6. Obtain the probability that he must stop at both signals. First question. The second question, at the first signal but not at the second signal. Third one, at exactly one signal. In this problem, a motorist is going to attend his duties. He is having the intersection of two traffic signals. The first signal, the probability he must stop at the first signal. When he is going to the duty, he is having the two signals are there. The probability of stop at the first signal is 0.4. The probability of start at the second signal is 0.5. The probability of stop at least one of two signals. One of two signals is 0.6. What he has given? Let us consider the probability at the stop at signal 1, which is A. Let the event A be. See, let the event A be. Let A be the event that the person stops at the first signal. Let capital B be the event that person stops at the second signal. Given probabilities. The probability stopping at the first signal is 0.4 he has given. The probability the person stops at the second signal is 0.5. The probability at least one now. At least one means A union B, which is 0.6. Next, stops at the both signals. Both means intersection of both of them. Both means intersection. A intersection B you have to compute. That is probability of A intersection B is required. But from the addition theorem we know that P of A union B, which is equal to P of A plus P of B plus minus P of A intersection B. This is From this, I wanted to write down P of A intersection B equal to. Now I am taking this part on the left hand side. I am taking the P of A union B part on the right hand side. When you take that like this way, now your formula will become P of A intersection B, which is equal to P of A plus P of B minus P of A union B. As you know, P of A is 0.4, P of B is 0.5, and P of A union B is 0.6, which is 0.9 minus 0.6, which is the answer is 0.3. That means at the both signal, the probability of a person who is going to be stopped at the both signals are 0.3. In the second one, stop at the first signal but not the second. Stop at only first signal but not the second. Stop at the first signal event is we consider as an event A, and not stop at the second is a B at A but not B, which means complement. You have to take it intersection. Right, okay? P of A intersection B complement you have to take it. Now, that is P of A intersection B complement. As I give the formula in the previous problems, that is P of A intersection B complement, which is equal to P of A minus P of A intersection B. P of A 0.40, P of A intersection B we know 0.30 from the previous one, which is equal to 0.10. The person whose the probability that the person stops at signal 1 but not at the signal 2 is 0.10. Stops at exactly one signal. Stops at exactly one signal means you may stop the first signal or the second signal. What is the you will stop at the first signal only. First signal means at the first signal but not the second one. At the second signal only means you will not stop at the first signal, you will stop at the only second signal. Which are the both events you have to take it as an addition. Okay, at exactly one only. This is the exactly one case. This is you may stop at the first signal but not the second one. But you may stop at the second signal but not at the first signal. So what is the formula P of A intersection B complement, which is equal to P of A minus P of A intersection B. P of A intersection A complement B equal to P of B minus P of A intersection B. Again, all these values we know. P of A 0.4 and P of A intersection B 0.3. Here also very similar. P of B is 0.5 and P of A intersection B equal to 0.3. When you solve this one, you will get exactly at one signal. The probability of stop at exactly one signal is 0.30. Find the probability of example 4. Find the probability of drawing a black card or a king from a well-shuffled pack of 52 cards. In this problem, we have to black card you have to draw, or a king. A black card or a king you have to draw. How many black cards are there? There will be 26 black cards in the pack of cards, and there will be 4 kings out of 52 cards. Now how we are going to select the cards? Let us see. Now let capital A and B be the events such that A is drawing a black card and B is drawing a king. The total number of cards n of s equal to 52. Now number of black cards are 26. As I told you, n of A equal to 26. N of B, number of kings, that is 4. Number of black cards, black kings, which is number of A intersection B. There will be out of 4 kings, there will be 2 black kings and 2 red kings. That is the intersection. If we take the intersection of both of them, which is A intersection B, which is equal to number of the items is 2. Now probability of getting the black card. First one, probability of getting the black card. There are 26 cards are there. Now in the 26 by 52, which is equal to 1 by 2 is the probability. Probability of getting only black card. Probability of getting the king. That is P of n of B divided by n of S. There are 4 kings are there. That is probability of getting king from the 52 cards is 4 by 52, which is 1 by 13. Now drawing a black king. Drawing a black king is you have to select P of A intersection B. Okay, drawing a black king only. Black king. There will be only 2 kings which are black. Okay, now you take the intersection of both of them. The intersection of both values are 2 divided by 52, which is equal to 1 by 26. And drawing a black card or a king, which is A union B. Drawing a black card is P of A. Drawing a the kings are P of B. Drawing a both of them black kings, both, which is the formula P of A union B, which is equal to P of A plus P of B minus P of A intersection B. How you know P of A? We calculated that is 1 by 2. We know P of B, we calculated that is 1 by 13. And P of A intersection B already we calculated that is 1 by 26. When we solve this one, now we will get 7 by 13.